Let's look at permeability equations for diffusion in solids. So you'd find that sometimes experimental data for diffusion of gases in solids are not given as diffusivities and solubilities, but it's obtained as permeabilities, which is our PM there, in m cubed of solid gas diffusing per second per square meter cross sectional area. So this will be through a solid 1 meter thick under a pressure difference of 1 atm. And this permeability can be related to Fick's equation as follows. So Na dAB Ca1 minus Ca2 over Z2. So this is the Fick's law. So this is Fick's law. There. Right. But remember the relationship between concentration and solubility, SPA over 22.414. And Ca2 is SPA2 over 22.414 there. Then substituting 1.52 this into 1.59, this one you want to substitute it into 1.52 there. To obtain the following. So we just go and replace where Ca1 is. So where this Ca1 is, you replace it with that. And where Ca2 is, we replace it with that. Right, after that, we obtain the following equation. Then we need to define now PM is equal to DAB S, so that our equation is converted to that form. So continuing with diffusion in solids, and us finding that that is where our permeability PM is given as DABS. So let's look at an example problem. A polyethylene film 0.15 millimeter thick is being considered for use in packaging a pharmaceutical product at 30 degrees. If the partial pressure of oxygen outside is 0.21 atmospheres and inside the package it is 0.01 atmospheres, calculate the diffusion flux of oxygen at steady state. Use permeability data from table. Assume that the resistance to diffusion outside the film and inside are negligible compared to resistance of the film. So that's diffusivity data, and we're looking for data for oxygen, where we have permeability there, where we have permeability, this is our, for the permeability there, right, so going to the solution there, so let's look at table 1.51, permeability there, solute STS. So let's just go back a bit. And look for our value there. We need to look at the compounds. So we are talking about polyethylene. Right, so from the graphs, this is where we have our polyethylene. So this is where we have our polyethylene, and this is where we have our oxygen, and we don't have solubility data there. We also don't have diffusion coefficient data there. So we get that value as indicated there, 417. So this value is what we then use to calculate so this is the value we use to calculate. As indicated, our PA1, PA2 is there, the thickness is known. Then all we need is to substitute and obtain our value there as indicated there. So this is the value we are getting there as indicated there.